Yeah. Well, since that was a video recording, there will be no Q&A, unfortunately. Anyway, that was a great talk. Um, all right. Next, I will be briefly presenting what kind of foundational models that we are building at INSAIT. Professor Durbikan told me that if you expose your belly, people believe you more. So I'm here. Uh, so it's gonna be quite teaser, not really a proper talk. If you have any questions now, you feel free to interrupt me. Or I'm here in Sofia anyway, so drop me an email or come to my office. I'm always happy to discuss. My name is Danda Paudel. I'm a faculty here at INSAIT for about 2 years and a little bit more, working in computer vision on different topics. Today's talk's topic is Earth observation with multimodal models, specific focus on temporal and reasoning aspects. As I said, it's going to be a teaser, and more importantly that it's going to be quite good overlap thanks to previous speakers, that a lot of content that I have will be easier to explain, or I can go very, very quickly. Yeah, so me and our team at INSAIT who work in computer vision are interested in all kind of visual data. Visual data primarily in the form of images, videos, or other form of visual data like point clouds or SAR and many other things coming from all sorts of visual data capturing devices. Here in these settings, those would be that images coming from space or aerial flights or ground devices or other data sources like from the internet, surveillance cameras, body cameras, any kind of visual data recording device, and then video are of our interest, broadly speaking, for the computer vision team at INSAIT. Going from the data source to the data itself, that we already saw today that there are various kinds of data types. Examples of the LiDAR, SAR, synthetic aperture radar. This is the hyperspectral image. This is the image collections from the internet. This is supposed to represent the video frames. This is 3D scenes, point clouds in this form. Audio, and then these are the visual data, and then what we believe is that such kind of not only the temporal links of the visual data, they tie the information together, but also at times the text and then audio also tie these visual data together, and therefore they also automatically become of our interest to process. That makes it very, very multimodal data, and as also discussed previously, these data are like huge in size, and they require heavy in computations. We would like to build foundation models, for which I will come a little bit more in details later, but by now should not be anything new for you at what foundation models are, and that should be able to do multimodal processing, and more importantly also should be able to do mostly live inference and possibly also update itself in a very live setting so that it can cope up with new circumstances much more better online. Doing so would enable many applications. These are just to name few. Could be the Earth observations, the topic of the symposium today, and could also be the autonomous vehicles, also about the urban planning and disaster management. In some sense, broadly speaking, we are interested to put them all together, all sorts of data, putting them all together. that data that you are capturing maybe from the autonomous cars could possibly be connected to Earth observations. Data that you are capturing for urban planning could also be possibly connected to disaster management. That is more of the holy grail, I would say. Today's presentation, although, would be focusing on Earth observation and disaster management more as a teacher, as I said before. So just as an example, this is already the statistics slightly old, few years old statistics. If you look into the images captured by Landsat, Sentinel-1 or Sentinel-2, there are tens of millions of images. These images are huge. We're talking about one image means it would be about 100 times 100 kilometers times 100 kilometers area, with each pixel covering about 30 meters resolutions or higher, right? Such kind of data, the visual data itself, are available in terms of petabytes. But as the title suggests, having data does not mean having the insights that the data offers. The data itself has its own different types. 3 primary types of data that we're interested are the spatial, temporal, and spectral. Spatial data is basically the space that it captures, just like your Google Earth. That would be the spatial data. Temporal data would be about changing over time. That same Google Earth doesn't remain the same over time, right? So then you have to study how the data or the visual data changes over time. As well as spectral, at times what you can see using the regular RGB cameras is limited, that you cannot see through the cloud, you cannot see through the fog, but some sensors do allow you to see much better also in these difficult circumstances, like night vision can actually make you see in the night, right? Therefore, different data will serve different visual purposes. And for that, we'd like to build models that would leverage this data set so that we can derive the insights. Essentially, just having data is not what offers us the insight, but building model and analyzing them is what builds the insights, and this is what is needed, and this is what we call the new generation of AI model for space. Slightly more in details, that just wanted to give these different branches of the data example types. Here is the optical one, this is the radar, this is the hyperspectral, and so on and so forth. This is the radar, is also the SAR, what I mean to say. All this data will get collected by different physical processes, and I'm highlighting these physical processes mostly because these are tailored to capture a particular kind of information that they often being complementary to the others. Such complementary informations can arrive, to you, and now big question is how to process them so that we can derive insight from the data, massive amount of data that could be possibly collected or have already been collected. In this attempt of answering these big questions is actually the part of this symposium, that how to build such models that can actually consume various kind of data types in foundation model settings. And here is our attempt together with many collaborators, that what we call the EarthMind is one of the foundation models that we've been working together on the space data that can consume different kind of visual data as I presented before, and also perform different kind of tasks to derive the insights that we are looking for. Here in this example, these fine-grained perceptions of the image captioning, not sure if you can read it well, but yeah, these are these different examples, each of these tasks in the fine-grained perceptions, image captioning, referring expression segmentations, object counting are these different tasks, one set of tasks that you can do. Other tasks could be spatial reasoning. Also the causal reasoning of the task. For the disaster, here examples I include disaster forecasting and urban assessment and coarse grain perceptions. These are different tasks that we benchmark ourselves within the Earthmind settings, and Earthmind also offers a model. This model takes, this is the optical image, sorry for the resolution, this is the optical image, this is the SAR, synthetic aperture radar, this is the multispectral image. All these can go into this model, and these are the pre-trained encoder models trained in this contrastive fashions, as previously Aaron talked about. And then this data goes through this vision language projector to eventually align with the large language models. Here, the foundation model we're talking about is a vision language foundation models, where it's not only about the vision components. The vision component goes into the language models. They somehow get aligned, and then therefore you can do co-piloting much more better. Actually, if you get output only from the language model, you get output in the language settings, and at times you are also interested in the visual outputs. For those visual output, here you have this mask decoder. This mask decoder takes the outputs from both the image encoder as well as the output from the language, and somehow fuses them together to get the visual outputs. Here is the segmentation mask that you can see here. It's more part of the model design, or contribution or hard task is to develop these cross-modal fusions. This is basically the block here, the details of this block, and this is the spatial attention prompting. This is the block over here. This model helps to fuse this information from different sensors better. I will not go through the details. Here, this model actually helps your language models to talk to your vision decoder better by offering these exchanges between their attention layers, making it more accessible. The model train uses inter-BL2 as a BLM, and then SAM2 as the encoder-decoder backbones. So for this intern, BL has these video encoders. This video encoder has been leveraged to do these extensions to this multimodal for both SAR as well as of the multispectral inputs. These are the more of the details on this, how the cross-modal fusions are used for the multimodalities, and then how the special attention prompting helps to talk to the LLMs better. This was one of the early works that we did with many collaborators, and then from there we have continued addressing the limitations of this model, the Earthmind, and what we call EarthX. Earthmind limits itself in regard to not being able to process temporal data successfully, as well as the high resolution data. The temporal data, these are the different slices over the time that this XY axis, the spatial dimensions, and this is the time axis. And when you acquire images from the satellites at one locations, you can acquire at the same locations at a different instance of time. This is what the chunk of data that you can get. This data, if you look into a particular area, could be of higher resolutions, and the Earthmind, which was state of the art at its time, could not process such kind of temporal data or temporal reasoning, more specifically multi-temporal reasoning that Alex also mentioned this morning, could not do. as well as could not actually process large scale images. When we are talking about large scale images, here we're talking about 4K resolution. These are the two extensions that we have done in OrthX, that is the upcoming model, soon to be released, still evaluating, but I'm going to share some early results today. So essentially how it enables is by these new extensions, where one of the key things that we go for is that hybrid contextual tiling, and that's what allows us to do better high resolution reasoning. At the same time, we make use of these video models. Actually, it's a fairly easy way, I would say, at least for the baseline, that video models of video VLMs are indeed quite well adapted, at least for the comparable to the state-of-the-art results, quite well adapted to do the temporal, multi-temporal reasoning in the spatial settings as well. What we did was we used a TioChat. That is one of the benchmark for multi-temporal reasoning that Alex also presented this morning. This is one of the state-of-the-art models in TioChat itself, been trained on TioChat benchmark and the dataset. We train our text on TioChat benchmark and then obtain the results. I guess it's not going to be easy to read. Here is the TioChat. Here is the OrthX. And these are the numbers. I think numbers are not that important. Here you can see at the bar, lighter the better, darker is the worse. And then among these two columns, here these different characters that you can see here, that means different task, the temporal task that you are doing. And then we are comparing directly against TioChat. And this red checks means that this particular task, which model wins. I would not make a claim that we are doing essentially much better than TioChat, because evaluations are yet to be done in a full scale. But what I can fairly say is they are comparable. But the good news is that TioChat, the one model we're comparing, is a state-of-the-art. While being state-of-the-art, is actually specialized models. Specialized models means that it can only, for these settings, process only temporal data, not the other modalities, and this is temporal in the RGB optical settings. Whereas the model OrthX can process everything that EarthMine could process, plus high resolution images, as well as the temporal data. While doing all that together, it is competing or comparable to the state-of-the-art temporal or multi-temporal reasoning model TioChat. Since I said that OrthX can do everything that EarthMine can do, we did evaluate it on optical SAR as well as optical plus SAR. I'm just presenting only one result here on two different settings. Okay, this is going to be difficult to explain. Okay, this is the radar plot. Suppose this has axes here. Wherever these lines are broken, that means there are axes here. Along this axis means that there are different tasks of multi-temporal reasoning, and then yellow dotted lines belongs to the EarthMine, previous state-of-the-art in these settings, and then the blue one is the OrthX that I'm describing, the model that we are developing and yet to be published. You can see it here clearly that almost in all the settings that the blue lines is outside means better, then the yellow dotted lines of the EarthMine. Same thing goes in the another settings of the evaluations when comparing against EarthMine. OrthX wins in most of the settings, most of the times. Now I'll change the gear a bit, and we also discussed this morning, or so far, that just building the foundation model is not everything to solve complex tasks. To solve complex tasks, we'll have to leverage them in some way of agentic manner, or some way of doing multi inference or multi-reasoning and multi-steps, as you call. I'll call it agent for short. Then these models, foundation models, are supposed to be used in agentic manner. Agentic manner, for those who don't know, it could be thought as the thinking mode of ChatGPT. Yeah, so that we been testing for this task of the disaster prevention for the wildfires. These disaster wildfires is particularly of interest because knowing if any particular location is has high risk has many factors to consider. You cannot just look at to one particular things. You need to look into the topology of that space, the climate, and then many other aspects that has to do with the land cover, that what's there exactly, what kind of fuel types are there. And so many things needs to be taken into consideration to come to the conclusion whether or not you should buy a house in that region because it may be too much fire prone. For this, we've been using this data set provided by the US agriculture departments. They do this wildfire modeling by the experts in USA. Here, the red means high risk, and darker means the high risk, and lighter means the lower risk. I guess one can see around this California regions that everybody knows that things are risky because of the weather as well as the land cover or many other factors that matters. Seems like the west of western of USA is more risky than the east part. These are the rasters provided by the experts, and what we are trying to do is trying to not use this during the inference, but trying to use this during the training. The agents, we train the agents on this data, and then trying to predict wherever maybe you are not making the predictions over here where this data is not made available. So this all we are doing based on the facts that matters to make the predictions for the wildfire risk prediction. So given these particular regions of the interest, some data has been prepared to feed it to the foundation models, what we call the FireScope AI agent. On the FireScope AI agent, more details will be presented by Mario tomorrow at the Spotlight Talks. So I'll skip over the details for now. But the idea is that you start from a geospatial data and then somehow prepare your data to fit into your foundation models. And these foundation models will be trained using GRPO algorithms. That's essentially an algorithm of doing reinforcement learning for vision language foundation models. That's what we are doing. To come with this chain of thoughts that not only about, this is the final scores that how risky is this particular area for the fire to catch, right? Then it goes to this chain of thoughts, gives you this interpretable results, at the same time gives you the score that in this particular example is 8 out of 10. What we did is that we evaluated this against GPT-5. We provided the same information to GPT-5 as well as the model that we trained ourselves for this particular task. Here are 3 metric. Among these 3 metric, mean absolute error and mean square error are essentially the error, so lower the better. And this KWK is actually the agreement score. So the agreement higher, the agreement better it is. So in these two bars, that green is the FireScope, the model that we are developing. Blue is the GPT-5. And in both the settings, that whenever the lower is better, then our model is low. Whenever the higher is better, our model is high. Only after plotting these results, I realized that this is not the best way of visualizing metrics, that some being higher better, some being lower better. in the same plot, but these are the very fresh results, so this is what I have to present. Sorry for the confusion if there is any, but the takeaway is that in all the three metric that model that we have trained in-house using this GRPO for RL is clearly better than GPT-5 under same circumstances. All right, last but not the least, that we been working on doing the visual understanding, not only using the GPUs, but also the edge devices. And I would like to present that here, mostly in the context of data analysis, not only on your large GPUs, but also maybe on the satellites directly, and or on the edge devices, what I call is not a GPU. Right? When I say so not a GPU, it means whenever in the satellites, if you want to, let's say, acquire SAR data, we've been talking about SAR data quite a lot, then it goes to different steps of processing. Initially, you get some raw data that makes no sense. This is the SAR raw data, right? And then your interest might be to know whether there is ice in this particular area, right? And this is what we call the ice classification. You may want to do so because, I mean, you want to know early enough because many times that these information that you gather may not be of any use. So you just want to discard so that you don't use bandwidth to do the communication. That you want to do early enough, and unfortunately in many satellites, especially the small satellites, that there is no enough lifting capability to plug in the GPUs, let alone doing this power supply. So you want to do those in a much more low computing settings, so low power settings. And in this SAR pipeline, that this is how the image gets forms, and all these image formations steps do get done already on the edge, because when you are transmitting images, these steps actually gets done on the satellites, and then together with many collaborators in these particular projects, DLR, Uvotica, EOPKI. So we've been exploring into this doing computation directly on the edge. We're not particularly exactly contributing on these settings, but we've been contributing more on the foundation models to become next. How we can deploy foundation models directly on the satellite so that all these Earth observation tasks could also become easier. This is for the ice classification pipeline using the SAR data, and this is the examples of doing compute directly on the edge for the object detections. Here, the ships are being detected. Well, again, these are the tiny red dots. Maybe you can see it better. The many red dots are basically bounding boxes for the ships that have been detected at different locations. These have been done directly on the edge devices. When we talk about the edge devices, we're talking about devices similar to Orin Nano. In the Orin Nano would cost you about $250 in contrast to tens of thousands for proper GPUs. Idea is to eventually bring to you tiny ML kind of devices that would cost only $10, and also the power would be only 165 milliwatt. So those are the devices that we're aiming for, but currently we are deploying models on these kind of devices. This we are doing in a project called the Edge AI. This is a European project where we are contributing by bringing these multitasking foundation models that does the visual task. Here we are showing the examples in the generic settings, but the idea is that this is also a foundation models that can do multiple multitaskings, actually based on Dino V2, and currently we are working towards the Dino V3. And this can take images and then do the multiple tasks. Here the semantic segmentations, instance segmentation, depth predictions, object detections, and human pose estimation. such kind of models that you are building and deploying directly on such kind of devices, which is the Jetson Orion. And we're hoping to do so also for now the smart phones, so that such kind of foundation models to do early tasks can eventually be brought onto the edge. The idea and potential idea is also to bring that edge computing to the satellites, so that satellites don't have to carry the GPUs or supply the power to the GPUs. With that, I come towards the end. I talked about the kind of data, the kind of data that we would like to process, the kind of models that we are developing, and kind of insights that we are interested. Last but not the least, that the next thing what we want to do is doing these ground data integrations, that eventually we also talked about this integrating the map today, but those maps, the ground maps, may come in the form of the 3D models or digital twins, 3D models, so on and so forth. That's what we are looking into. And other things that we're looking into is long-range dependency and complex reasoning. That if something happens in one particular locations, you want to know the cause and effects that may have caused from some other locations. For example, if the water is polluted in a particular river, that may be because a factory is not doing its due diligence or duties properly somewhere along the line, and that's the factory that's polluting, or any farming area has been leaking the pesticides, things like that. And the third thing that we are looking into is to process the even larger volumes and new types of data. And one example of such data would be the hyperspectral images. Hyperspectral images can go as far with the current technology that you can capture images with like 9,000 channels. Each channels would represent one particular frequency in the light spectrum. With that, I would like to end my talk. If you have any questions, I'm happy to answer. Thank you very much. No question?
If currently there are no questions, or is there?
Is there any question? Well, seems like everything is clear.
Then I can directly
Please,
ask actually one. So about VLMs, specifically, what is the challenge that the VLMs for geospatial data bring in there? So why do we need special architectures and special solutions, and can just address with some more generic VLM?
I think it's mostly because of the type of data that it comes with. Because when you are getting the data for the Earth observations, it's usually not under your control that what kind of camera, what kind of devices you want to deploy. When you want to deploy, like if you want to capture some high resolution images somewhere in, let's say, Vitosa, even if you pay money now, you may only get after 4 days. So such kind of circumstances that you have to live with, the what resolution that you can get access to, as you are, even if the devices exist, you may not have permissions to capture them, or also that the publicly available data sets, they actually can capture somewhere between one image per 5 days to one image per 16 days and stuff like that. These are not under your control, and they come at different times, and then the interest of the task or the events that you're interested may not really come, as per your desire of the data captures, of the type of the data, or the time of the data, or the resolution of the data. And that's the, I think, hardest part that one needs to look at least from our viewpoint, looked at to develop the systems much more differently than homogeneous systems that we are talking about in VLM settings.
Thank you. Other questions?
Nice presentation, thank you so much. I wanted to ask, in multimodality, like different satellites have different resolution. So during the fusion of those satellite images, like what normalization measures you are taking into like considering? Because maybe some, if you're taking some lens at NDVI or some other humidity or soil moisture, they have their own satellites and they have their own resolutions. So, but when we fuse it, are we keeping it in mind that all the resolutions of each of the modality are same, or we directly fuse them?
Oh, that's a good question. Actually, the way I see is it has to be more of the meta fusion than direct fusion. So your model is aware of what it's receiving, and therefore it makes the decisions how to fuse them. So it takes kind of the informations about where the data coming from, what kind of data is coming, right? And therefore it itself tweaks in some way that how to fuse them so that it can derive the most useful information out of it. So if you are trying to do it much more blindly, likely it's not gonna do a great job, or it just becomes a lot of tasks coming back to you. Instead, what we should be striving for is to find such kind of meta algorithm, so as to say, for the lack of the better words, that it will take the specification of the sensors, locations of sensors, time, and everything, right? And then decides how these needs to be fused together or kept together, maybe not even fused, right? And then used during the downstream task or reasoning process.
Okay, thank you.
Welcome.
Thank you for the presentation. In the first slides, you mentioned that one of your goals is live updates. Could you elaborate more about this online learning aspect of the models that you develop?
So this is one of the need that we recognize, that it needs to have the live updates. This is not the part of the model that we currently have, right? So the live updates, I mean, there are two aspects of the liveness. One thing is about just being able to do this online inference quickly, right? That's one of the aspects. And also that if you are doing this large volume processing, you may not afford to do this one-step online processing. But then more harder problem is essentially this, try to do this adjustable network parameters that would automatically learn over time. It has to be more on this continual learning settings that we are looking at, not precisely in this context, but what you are looking at in this other context of the learning is the continual learning, that is data get exposed, then it has to be automatically cope up with over time without forgetting that it has what it had learned before, right? And this you have to want to somehow avoid this catastrophic forgetting problem, at the same time be able to learn things continually over time. That's what we are looking at, and that's what we want to bring into these foundation models over the course of the time.
But do you have some specific approaches in mind to use?
So currently, one of the approach that we are making towards the continual learning, slightly different settings, as I said before, is using this mixture of experts, that you learn this mixture of experts on, because the idea is that over the period of the time, what new things you get exposed, you possibly might have get exposed to before too. You just have to know that what different circumstances that you have exposed now, and therefore you categorize them into different experts would be able to process them. And whenever the new data comes in, then you have to map it to what experts you have learned before, right? Therefore, you stream your data, to the different experts, so that you can retain the performance, at the same time be able to analyze something new. And then the updates from the new data in this continuous settings will only go to that particular experts, either the existing experts of that category, or you create new experts.
So you compartmentalize the data using different experts, different models.
Absolutely, yeah. And then you just, that way it avoids, you only learn for that particular context using different experts, and don't touch the other experts. And if you are exposed to new contexts next time, right, then you will not be contaminated, and therefore won't be the catastrophic forgetting problem.
Okay, thank you very much.
Further questions?
All right, so if there are no more questions, thanks, Annie. So then we are also end of these sessions. Then this is going to be coffee break after this. And after the coffee break, there will be the talk, last talk of the day, that will start at 4:40. See you then. Thank you very much.